the start of period 2. Don't worry if you took a bit longer than 35 minutes to complete period 1. You'll have more time in period 3 you'll have some more time, around 10 minutes, to just complete or finish off period 1 and period 2 if you didn't get to do it. So don't worry about that. Okay, so in last lesson we looked at exothermic and endothermic reactions. And this lesson we're going to look at how we can measure whether a reaction is exothermic or endothermic, and we do that using calorimetry. And calor, that comes from the Italian word heat, as the Latin word, sorry, heat, and metry relates to measuring. So we're kind of measuring heat here, and once we measure the heat energy that is released or absorbed from a reaction mixture, then we can work out whether it's exothermic and endothermic, and we can then work out how many joules of heat energy is kind of emitted or absorbed, and then from that we can work out the enthalpy change in kilojoules per mole. So we can work out how many moles and then the enthalpy change, which is in kilojoules per mole. So we use a calorimeter, and this is a calorimeter here in Onyx. And just as a recap, we can measure the temperature change in degrees Celsius of a reaction using calorimetry. Okay. Calorimetry is the measuring of the temperature change in a reaction, and we measure the temperature of the reaction before and after. We're measuring the reaction mixture here. The calorimeter in this case is it's these two cups which are nested together. Normally we use in a lab we'll probably use just one cup and just use a beaker just to stabilize it. But you've got two cups here, and that just provides better insulation. And then we've got a lid here which also provides insulation, and that just prevents heat energy from escaping. So this is your calorimeter. From the temperature change, which we measure before and after, we can then work out the energy in joules, and that will be next lesson, like next week. That has been transferred to the bonds or to the surroundings. So we can work out whether it's exothermic or endothermic, and again we'll be looking at that next lesson. I just want you to watch the calorimetry in practice, or the polystyrene calorimetry in practice. So just watch this video, and you only need to watch to 3:18. You don't need to watch anything after that, but you can if you want. It will help, and it's only another minute and a half, but up to you. And think about the following questions: why is a polystyrene cup used? Why is the polystyrene cup put into a beaker? Why is the lid used? And why do we take the temperature before and after? So just think about. Okay, so these are your answers. You didn't need to write them down. Just having to think about them. Why is a polystyrene cup used? And that's because it's an insulator, so it reduces heat loss. It doesn't prevent it fully; it just reduces it. A polystyrene cup into a beaker, and that's just to stabilize it. The thermometer can be quite heavy, and sometimes it can tip over. A lid is used to reduce heat loss again, so the lid is also an insulator to some extent, not as good as the polystyrene insulator, but it is an insulator nevertheless. And why do we take the temperature before and after? And that's so we can measure the change in temperature. If we don't take the temperature before, then we can't say for accurate what the temperature is. We can probably guess and say it was probably at room temperature, but it's better to just do it. It's better to just measure it. And you do need to give the thermometer. You need to give the thermometer some time to reset there between each reaction. So just have a read of this next two slides. It might not take you 10 minutes, probably a bit quicker, but in class, this is the practical that we would have done. And it's measuring the temperature change using a simple calorimeter. And this is our simple calorimeter here. It's a beaker, polystyrene cup, and a thermometer. You can use the thermometer to stir, so you don't need a stirrer, but just be careful here because the thermometer can sometimes break the polystyrene cup if you're a bit too hard. So try to be careful there. So you will measure the temperature change for some chemical reactions and interpret the results. You will carry out 4 different reactions, and then you'll be measuring the temperature before and after. And this is a glass measuring cylinder, and that is more accurate than a plastic one. That's just because plastic can warp and bend and things, but glass can't. So tips here: use the thermometer gently when stirring to protect the polystyrene cup. rinse the measuring cylinder, a calorimeter. You also want to dry it as well, and between each use. So you've got 4 different reactions. You'll use the same calorimeter. You'd want to wash it between each reaction and dry with a paper towel. And avoid getting any of the reaction mixture on your hands, because you've got copper sulfate, which is a bit of an irritant to the skin. So avoid getting on hands, and wipe spills, and wear gloves. Wear goggles, sorry. You don't have to wear gloves, but you can do an extra precaution there. And read from the meniscus when you are using your measuring cylinder here. And in the video, you do see him reading from the meniscus when he does do it dropwise after. And here's the reason why. And this error here, if you don't read from the meniscus, you do get a slight error in your reading. So you've got to read it kind of head on, like parallel to the surface here. And this is actually called parallax error. Parallax relating to parallel, and the error, of course. So very important there. So these are the 4 reactions that you'll be doing. You can pause and read them. I'm not going to read them now, but I've summarized these in a table, so it's probably a bit easier in the table that I'm going to show you on the next slide. So here's a summary of the reactions. For reaction 1, it's just 5 centimeters of water. You take the temperature and then add a spatula of anhydrous copper 2 sulfate powder, then take the temperature after. And you take the temperature, you record the temperature which it finally reaches. So when it stops increasing or decreasing, that's when you take the temperature, when it stopped moving. That's the final temperature you record, sorry. And you do the same for each of these. Again, you can read them. With your results, please do copy and complete. So copy and complete these, and then you can work out the temperature changes, and then whether it's exothermic or endothermic. And this is a bit harder. I've added in another column here. Please do add that in your books. It won't be there, but please do add it in and see if you can get those. If you can't, that's fine at this stage. So here are your answers here, and your temperature change here for your endothermic is minus, so do include your minus there. So maybe there should be brackets in these temperature with the degrees Celsius here. So we've got exothermic for the first 3 and endothermic, and that's because it feels colder, the temperature has dropped here, so it's endothermic. The type of reaction here, dissolving, displacement, and neutralization. Now dissolving isn't normally a reaction, but like if you dissolve sugar or salt, that reaction is not happening, but in this case there is a reaction happening. Your salt is being I think it's being hydrated here, so that this is a type of reaction. Your salt now has a different chemical formula. It has water molecules as part of the chemical reaction, part of the chemical formula, sorry. Okay, so in your experiment book, page 29 to 30, please do complete these questions. It'll take about 10 minutes. Pause now and just work your way through them quite as quick as you can. Come back to them after, but do time yourself. It's good to use a timer, actually. That can really help control your time. Now, if you don't have access to your experiment book, please do just take screenshots of this. And you might want to Google how to screenshot or screen grab on your laptop. Yeah, just screen grab them and put them into your OneNote directly, and just type over them if you want to, or answer the questions on paper in your book or whatever is suitable. For question 5, you can write word or balanced symbol equations. If you are using symbol equations, they have to be balanced. Okay, so in your experiment 3, this is an exothermic reaction, and your chemical energy, remember this is chemical energy here, you can write that at the side there if it helps. Chemical energy of the reactants, and that's high. When it reacts, your chemical energy is converted to heat energy, and that's being released to the environment, to the reaction mixture and the container and the air around it, the environment, and your products therefore have a lower chemical energy than before. Okay, so your chemical energy, some chemical energy is being converted to heat, and the rest of the chemical energy here, which is left in the products, but it's lower than before. Okay, so here in your experiment 4, that's an endothermic reaction. Your reactants have a low chemical energy. They absorb chemical energy from the environment, and your products therefore have higher chemical energy. Now your polystyrene cup improves the accuracy because it's an insulator, and it reduces heat loss. So experiments 1 to 3 can be improved by just using a lid, which is an insulator, and using a lid just reduces heat energy from being lost. So that helps there, that can help. And so how does the temperature rise in reaction 3? How is that affected if magnesium ribbon was used instead of magnesium powder? Now, magnesium ribbon has a larger surface, has a smaller surface area, so that means there's less particles. There's less particles exposed. So less particles exposed, therefore there's going to be less frequent successful collisions and a lower rate of reaction. So this gives more time for heat energy to escape from the reaction mixture. Although there's insulators around, the insulators don't stop or prevent, they just reduce. Okay. So experiments 2 and 3, both displacement reactions, with ones with magnesium displacing copper and the other ones with zinc displacing copper. So magnesium is higher in the reactivity series than zinc, therefore there's a larger temperature change between magnesium and copper than zinc and copper. That's just because the difference in reactions are a lot greater here. So write equations for reactions 3. These could be word or balanced chemical equations. I've written chemical equations, but you can easily convert them to word. It's copper sulfate plus water equals hydrated copper sulfate. Hydrated copper 2 sulfate, sorry, this is copper 2 sulfate. And then copper 2 sulfate plus zinc reacts to form zinc sulfate and copper. Copper 2 sulfate plus magnesium reacts to form magnesium sulfate and copper.